projectile how it will move. So it is going to move in a parabolic path. Then it will be almost like it will be moving vertically down. There's a one basic property of the viscous, like when it is striking here, no, it will be just descending vertically down. This what happens because of viscous drag. We are projected with a velocity u. This you can try. You can try take ball. You throw it, no. So when it's striking, almost it strikes the vertically. Prodded, what happened? The condition is like here. Viscous fluid. Here the air drag. The air drag is different than viscous fluid is different. In air drag, the viscosity is very less. So we don't see this particular thing. But if the viscous fluid is there, if you project it, it is going to strike vertically down. There's a one basic property. Previous problem also I shown. Almost after a long time, it will move with the terminal velocity. So just before striking, the particular ball will have a terminal velocity. It'll be moving with a terminal velocity and strike almost, it will be moving vertically down. There's one basic property of the moment of the projectile in a viscous fluid. In the air, we don't see this. I think you just go outside, if you throw ball, no, it may not strike here. The reason for that here, the viscous drag offered by the air is very less, but the fluid, it will offer a little bit more. The resistance is more. So therefore we put this condition. That's why the word fluid is brought here. If it were air, you need not to take this decision. So what is the basic condition here at the point of striking? Okay, let's do one thing. Somewhere at any instant of time, it will have velocity v. What are the forces that are acting? The weight mg. Then the viscous drag will act opposite to velocity. It should be Fe. This at origin, there's a point of projection. Origin will take it. There's a point of striking. This is any arbitrary point. No, so what is the necessity condition, right? At point of striking, the projectile moves almost vertically downwards and ends with a constant speed. Just terminal, it will attain terminal speed. So like a terminal attains terminal motion. So therefore, what we can write, mg is equal to the viscous drag is equal to what, like a k vt into m. So therefore, g equal to k vt. I think this is the thing which is going to help us a lot in the numerical, you see. Without this, I don't think so, not possible. And what is vt? Vt is called as terminal velocity. Let's get into the calculation part. So here, the object is here. So it will have velocity v. This will resolve the component of velocity vx, vy, mg. What are the viscous drag? The viscous drag also we are going to resolve. Fvx, Fvy. Because you look at the projectile motion, I think this is the best methodology, no? Apply the equations of motion along x, along y. Problem will become very simple. Or else you have to go for curvilinear path. This will be very difficult to analyze along the path. The motion, to describe the motion along the path, perpendicular to path, will be very difficult. We have to encounter a lot of calculations and we are going to enter into almost circular motion, curvilinear path. So instead, we are going for we can go for the accelerated motion along x and along y, because the kinematics we are much familiar. If you really wanted to write in a plane, motion in a plane, or say motion in a plane means how the equations will be m dv bar by dt equal to minus mg bar minus k v bar m. It will undergo retarding initially, so therefore that negative signs are brought here. This will be very difficult no, to work out in this particular form. So therefore we are going to break up the motion along x, along y. So motion along x-axis. So this should be equal to ax equal to fvx by m. Negative sign, it's undergo retardation. So what is the viscous drag is equal to k v x, this is m into m. AD is a drag into mass will become the viscous force. So the m will get eliminated. So we'll get minus kvx. This, let me write it as dvx by dt. I think almost all no, you can manage from here. dvx by vx minus k dt. What is k equal to? G by vt. Let's integrate this. Initial projection is ux. This initial projection, we'll take it ux, some other color. Yeah. And uy, this is ux and uy. So initial at t equals 0, it was projected with a velocity ux. At any instant of time, let it be vx. So this will become log of vx by ux equal to minus gt by vt. What is ux? Should be equal to u cos theta. So taking log on both sides. So like a sending log on other side, vx equal to u cos theta e to power of minus gt by vt. Vt is what we assumed it, no? So g by vt, what it should be equal to k. So the final expression will be u cos theta the k is something very important. For different shaped objects, different liquid, the value of k will be different. Look at now, the x component of velocity is going to decrease exponentially in the viscous drag. Without viscous drag, it will remain constant. Now, what do you expect the range? Will it increase or decrease? Will decrease, no? With viscous drag, without viscous drag, the range. With viscous drag, the range has to decrease. You can see from here. Similarly, we'll go for the y component of velocity. Just we have to manage with mathematics here, I feel. The initial part, if you can set that things, motion along x, along y, the rest all mathematics. First, we'll get the velocities, then I'll go for the coordinates. Okay, the velocity term, ay is equal to fvy by mg, no? may may equal to fvy minus mg, or this you will not be comfortable, let it be here. Ay, so this will be ay. Okay, let's what is fvy is equal to? Now the what we should write in place of this should be equal to Acceleration is this one, no? KVY into M into M. By VT will come here. K I'll replace as G by VT. Oh, we are going. Just wait. I think I have to simplify further. dVy by dt is equal to K, what we wrote? K as G by VT. This will be G if I take common. Vy by Vt plus 1. So this should not be there. Yeah, see this. Now we'll integrate this one. At t equals 0, the y component of velocity was uy. At any time t, let it be vy. Okay, this I have to simplify. No, this will become quotient of this will be log of. Just check. I'll directly write it. I just said. So what I took is like a Vt. I took common. Vy plus Vt will come. Vy plus Vt. And there should be uy plus Vt. And I'll write in Vy plus Vt, uy plus Vt. Okay, no, check it. After substituting all the limits, everything. We wanted expression for Vy, no? So let me send the log on. Uy plus Vt equal to e to power of this one. So now this will become Vy is equal to e to power of uy plus Vt e to power of minus gt Vt minus Vt. I think we can justify our answer. Put t equal to 0. We'll get uy only. This would be the expression for velocity of the projectile at any time t. Is it increasing or decreasing function? It's also a decreasing one. So when it strikes the ground, put t equal to infinity. It will strike with a terminal velocity. I think what I assumed is right. After long time, let's assume that after long time it will strike the ground. Put t equal to infinity. Let's put. So this quantity will become 0. Then what is Vy? It is going to strike the ground with a terminal velocity. This is the basic assumption of the projectile motion with viscous drag. I am making things clear. You or myself may not be known much, but practically there's a condition. A drag will offer very less viscosity. We don't see this, but if it is thrown in a liquid, no, we do see these conditions only. So therefore, in the liquid, he has mentioned specifically. Okay, after getting this velocity, now we have to go for the displacement. The position is asking. So what was the equation? I think I'll do it here only. It will be much easier. Dy is equal to uy plus Vt. This will integrate. We are going to get the expression for the position. Dy is equal to uy plus Vt. At t equals 0, it was at coordinate at t equals 0, the y coordinate was 0 at any time t, that the y coordinate be y. Solving this, we'll get the required equation. And that g by vt is what k. If you want, you can replace in the end. Anybody? I think it's a very lengthy equation. Huh? Exponential. So in place of g by vt, okay, we'll do one thing. We'll write it at corner. G by vt is equal to k. Where all needed, you can. In the end, we have to express in terms of k only our answer. Final equation, I'll write it. Uy is u sin theta, no? So this will become g by k square. I do have answer equal to 1 minus. This will be your y coordinate. So solving all, and you have to replace that vt equal to g by k in the final equation. Will end up with the condition. Similarly, we'll go for x coordinate. What is x coordinate? It was equal to Vx is equal to this. I think this will be much easier. Huh? Maybe the question is testing our patience. Nothing is there. Only the main idea, the first, the mg equal to viscous drag. When it's striking the ground, it will strike with a terminal velocity. I think that's the only thing which we were not aware. The rest, everything is mathematics and the strategy. Like whenever projectile motion comes, so there are two approaches are there. Describing a motion along the path perpendicular to path. There is nothing but you're going to land in curvilinear motion. Instead of this, what we preferred to express the motion along x, along y. This will be safer method. And the final answer, check once. Put t equal to infinity. U cos theta by k. Okay, so these are some answers what we can finally we ended up. So what is the methodology here? Whenever viscous drag comes, describe the motion perpendicular to the, so like along the x-axis, along the y-axis. I think this will be much easier method. I think we have done several problems with the viscous drag in various chapters. And in different chapters are there. So in the HAP, you can check the some best numericals is what I have dumped it. Problems related to viscosity here. So many applications are there, almost around some 20 numericals are there. We'll add these things also to that. So almost 30 best numericals are available. Practice some questions in the material, some objective questions. I think you'll be in a far better position. We'll go for the next question. This small correction reduces horizontal speed of the stone at a rate. This word is missing in the book. That's why I added up. You read entire question, reduces horizontal speed of the stone at a rate. So what is this entire the thing?